Hi, I'm Tong, a PhD student from Stanford University, and I would like to present our recent work on developing methods towards suggesting actionable interventions for wheel spinning students. This is joint work with our collaborator Andrea Yetten at the nonprofit charity War Child Holland and my advisor Emma Brunskill. To motivate the problem, I will first tell a real world story of a student in the intelligent tutoring system domain we consider in our work. In this story, different shapes represent different pedagogical activities. Red indicates an incorrect attempt, while green represents a correct attempt. For this student, the student has been doing well up until he reaches activity C. Then the student incorrectly attempts the problem 20 times. At this point, we can infer the student is probably stuck. However, what happens next is the student then attempts the activity 41 more times, until they finally answer the activity correctly. However, the student is not in the clear yet. They have progressed to the next activity, Activity D, and they struggle and attempt the activity 56 times before finally answering correctly and moving on. Somewhere along the line, the student became stuck and should have been given an intervention. In this work, our goal is to tackle this problem by automatically predicting interventions to help such students. The observed pattern of the student is referred to as wheel spinning. Wheel spinning is a term that has been coined in prior research and is defined as when a student repeatedly attempts and fails to learn a skill in an intelligent tutoring system, like in the story. Prior research has shown that wheel spinning is a common problem and occurs in the popular middle school mathematics intelligent tutoring systems, the cognitive algebra tutor and assessments. Researchers also found it occurs in the intelligent tutoring systems of other countries, namely the scatterplot tutor, which was used in the Philippines. In our work, we also found this behavior to occur in the real-world application we consider, which is the Can't Wait to Learn program of War Child Holland, and is also the domain where the real-world story came from. Can't Wait to Learn is a tablet-based educational game for teaching grades 1 through 3 literature and math to students in conflict-affected regions, and is currently rolled out in 6 different countries. In the program, students work through a linear sequence of activities that teaches them the concepts. It is meant to be a self-contained program for teaching the subjects and can be used as a standalone educational program in situations where formal education is especially hard to access, as well as a supplemental program in a formal classroom setting. Prior research studies found the program was able to result in increased psychological well-being, as well as positive learning outcomes in multiple different contexts. In the specific Can't Wait to Learn domain we consider in this work, Uganda reading, a majority of students are making good progress. However, some students are not making as much progress as desired, and these are the students we would like to help. Prior work in wheel spinning examined the prevalence of wheel spinning in various applications and focuses on creating models for predicting when a student will wheel spin, mostly with the motivation that the prediction will be helpful for teachers who can preemptively help the student before they wheel spin. However, there is not much work in predicting automated interventions, which is what we study in this work. We study this because in Can't Wait to Learn, once a student wheel spins, getting help is very difficult. In the classrooms where the Uganda program is used, the average class size is 114 students to a teacher. In these situations, it is very time-consuming for the student to wait for help. And for the teacher, it is not only time-consuming, but also extremely hard or impossible to help all students. Additionally, in out-of-school settings, the program is run by facilitators who may not even have the expertise to help students. Additionally, in the Uganda reading program, 51% of students wheel spin at least once. Because of all of this, simply predicting wheel spinning is not enough. Therefore, in this work, our goal is to create a method that not only predicts when a student will wheel spin, but also predicts interventions that can possibly be helpful. We additionally focus on interventions that can be automated in-game to suit the setting where the teacher may be unavailable to assist. Additionally, we would like our method to require only a small amount of expert input. So for example, not requiring an expert to label a large dataset of wheel-spinning student item pairs with a recommended intervention. To do this, we propose a method that uses explainable machine learning, and this, to our knowledge, is one of the first investigations of using explainable machine learning for educational technologies. Additionally, because running a user study is very time and resource consuming, especially in our context, In this work, our goal is to evaluate our method through simulations and through the real-world dataset along with expert input to first find good evidence that our method would work, which, for example, could be used for the approval of a user study. Our method consists of 4 steps. In the first step, we work together with an expert to create a feature set, a subset of which are actionable and have corresponding interventions. In the second step, we use those features and past student data from the system to train a machine learning model to predict wheel spinning. In our work, we specifically study XGBoost, but any method that outputs a probability would work. In the third step, in real time, as a student is working on an activity, we predict if the student will wheel spin or not. And if the student is predicted to wheel spin, we then execute the final step, which we use methods from explainable machine learning that can provide an attribution over features for individual predictions. We find the actionable feature with the highest attribution and select the corresponding intervention. Specifically in our work, we used Shapley values, but there are other methods that can be used. We will now go into more details on this last step and discuss why we use feature attribution methods and discuss how Shapley values are calculated. So why do we use feature attribution methods? We'll consider the example data point for a student working on an activity inspired by our Can't Wait to Learn domain. Consider the case when this data point has a predicted probability of wheel spinning of 0.75. Given that the student is predicted to wheel spin on this activity, to give us a clue of how to help the student before they start wheel spinning, we may ask the question, for this data point, which feature contributed most to the prediction? If we can answer this question, and the answer was the activity ID feature, then the activity may be redesigned. If it was the time since last played feature, then there might be forgetting effects, and the corresponding intervention could be to automatically diagnose the student knowledge level and place them accordingly. If it was the prerequisite 1 feature, then the corresponding intervention could be to have the student repractice prerequisite 1, and likewise for prerequisite 2. Well, we can in fact answer this question using feature attribution methods from machine learning, and specifically in this work we use Shapley values. Shapley values originated in game theory and provide an attribution that satisfies a few desirable properties that make up the definition of a fair attribution. First of all, the attribution over features given by Shapley values sums up to the difference of the prediction of the data point and the mean prediction over the whole dataset, the efficiency property. So if the mean probability of wheel spinning is 0.2, then the attribution over features would sum up to 0.75 minus 0.2, or 0.55. To give an example of a possible attribution that satisfies efficiency, let A denote the attribution to a feature. Then the following attribution will sum up to 0.55. Shapley values also satisfies additional nice properties. To give one example, the symmetry property, which states if 2 features contribute equally to the prediction, they will be given the same attribution. To give an example, consider the case where P2 and P1 were equally important prerequisites, and also equally difficult activities. Then, if in a different data point, P2 also had a value of 7, like P1, we would want P2 and P1 to have similar attributions, and the symmetry property guarantees this. We will now go into details of how Shapley values are calculated, and we will first give some terminology. We first have the set of features used. Let Fj be the jth feature, so for example, F1 would be the activity ID feature. We will refer to the attribution we want to calculate, the Shapley value of feature Fj on the prediction of xi, as Shap Fj xi. We also define a coalition of features as a subset of the feature set. For example, the coalitions in our example would be the empty set, all the unique sets with 1 item, all the unique sets with 2 items, all the unique sets with 3 items, and the whole set. We will let letter F refer to a coalition. We will also write xi compactly as the following. We define xif as xi modified to only have the values of features in F. So for example, xif for the F given above would be the following. We also define V as a function that takes in an x, either modified or not modified, and outputs a prediction. So for example, bxi, where xi is the original data point, would be the prediction of the model, or 0.75. With the terminology defined, we can now give the mathematical expression for Shapley values. Let C be the coalitions that do not contain Fj. The steps to calculate this expression is to calculate the amount Fj contributes to each coalition in C, then take the expected value over these calculations over all the coalitions in C. To give an example of calculating the contribution of Fj for one coalition, let Fj equals F3, or the prerequisite 1 feature, and let the coalition F be ID, P2. Then the coalition F union Fj is just F with Fj added, or ID P1, P2, with the corresponding modified data point. Consider the case when the prediction of the coalition without Fj is 0.1 and the prediction with Fj is 0.65. Then the contribution of Fj on this F is the difference, 0.55. It can be shown that the efficiency property, where the attributions over all the features sum up to the mean prediction, is satisfied. Additionally, intuitively, because each feature has the same number of coalitions that do not contain it, the symmetry property is satisfied. In machine learning applications, we want to use a machine learning model as V, the function that gives a prediction. However, in general, machine learning models cannot take in partial data points. So V is approximated by sampling a second data point from the dataset and substituting in the values from that second data point for features not in the coalition. So that was the details about step 4 of our method. For evaluation of our method, we compare with two baselines. Firstly, because we are using XGBoost for our prediction algorithm, one baseline is the single most important feature of the model. This will predict the same feature and corresponding intervention for all data points. So, for example, if the most important feature is prerequisite 1, always predicting prerequisite 1. In contrast, Shapley values provides this feature importance for each individual data point. So for example, predicting prerequisite 2 for some students, or prerequisite 1 for others, or time for others, and so on. A second baseline is logistic regression. Logistic regression is a linear model, so it has feature attribution for individual data points built in without requiring additional computation, such as computing Shapley values. However, in this work, we focus on methods that will work with nonlinear models, such as XGBoost or neural networks, as nonlinear models often have higher representation power and can achieve higher accuracy. We now discuss our results. For the simulations, we generally found our method was able to achieve high accuracy and perform better than baselines, as well as miss less students who needed interventions compared to baselines. Here we show the results for our second student model when the prediction is made at the 5th attempt. For our qualitative study in Can't Wait to Learn, we chose 6 cases randomly. We then asked an expert to give recommended interventions for the cases. We found our method was able to achieve the highest accuracy compared to the baselines, matching the expert prescription in 4 out of 6 cases. Looking closer at the cases, we found in the 2 cases where our method made a mistake. In one case, the expert recommendation was not in the list of possibilities for the algorithm. This was due to a potentially helpful feature not being included in the model because of limited data. As more data comes in, this could potentially be overcome. In the second case, an error was found in the prerequisite structure, which was important for informing the intervention. Overall, this analysis suggests our method can be promising if correct inputs are given. In conclusion, we proposed a method to predict actionable interventions for wheel spinning, and through simulations and a qualitative evaluation of the real-world dataset, found it can be promising. In simulations, our method was able to achieve high accuracy and perform better than baselines. In the Can't Wait to Learn case, our method demonstrated the ability to suggest interventions in line with what an expert would prescribe. And this, to our knowledge, is one of the first works in predicting interventions for wheel spinning, as well as using explainable machine learning in an educational technologies application. Our next step is to first investigate distilling our method to fit on low processing power tablets, and afterwards we would like to run a real-world study in the Can't Wait to Learn context. Thank you.